Good afternoon, everyone. My name is Mark, and I'm one of the researchers from the LUNAR Lab team. And we are really thrilled to be here presenting a progress update on the work that we've been doing to build what we hope will be the first foundation model for lunar resources. We've recently entered a new era where machine learning models can learn to perform a variety of tasks. Embracing this paradigm shift, we're very proud to unveil our multimodal foundation model for the moon. What you're seeing on the screen is a three-dimensional projection of our unified multimodal lunar embeddings, which are at the very core of our foundational model. In the next few minutes, we're going to tell you how we've achieved this and what this enables. The core problem we're facing and working on is that lunar data is siloed and unstructured. We have dozens of instruments, but no way to really see the full picture. This begs the question, how can we extract new insight from multiple lunar instruments? In other words, how can we combine multiple data modalities into a unified representation? Our approach is, as you may have already anticipated, a lunar foundation model, where we combine a number of global data sets, including multispectral, radar, temperature, and gravity sensors, using a multi-MAE architecture, which is a special flavor of a masked autoencoder, and this yields a global set of unified multimodal embeddings. With this, I hand over to my colleague Gauthier.
Thank you, Mark. So, as you said, we are using a multimodal masked autoencoder that we trained on reconstruction and translation tasks. So now let's see if our model, LUNAR FM, can actually be a translator from one modality to another one and check if it did learn useful information across modalities. To do so, we perform multi-modality reconstruction. What it means is that we start with some ground truth chips with all modalities. We then randomly mask out 90% across all modalities. So here, all that became black is masked out and not seen by the model. We do this in order to force the model to learn how to reconstruct each modality, but also across modalities. As you can see here, for instance, on the first column, only one patch is available for Grail. This means that the model will have to learn from the other modalities to be able to reconstruct this modality with only one patch. Now let's see how our model performs this reconstruction. And let's compare it with the ground truth. As you can see here, the reconstruction is qualitatively very meaningful, and we also added some quantitative measures by computing the mean square error. All this shows that our multi-masked autoencoder did learn valuable information, modality, and cross-modality wise. With this, we pushed further and also checked if our model learned some semantic understanding and can also provide interpretability. To do so, we first run some similarity search using our embedding. For that, we start with a location that is interesting to us, let's say lunar pits or crater rim or any other location like the one we show on this first column. This represents our input query. Then our model outputs the top 10 closest locations on the moon within our embedding. As you can see here, those 10 different locations are quite close to the initial query, which shows that our embedding is meaningful. We also went beyond to see if it can determine and provide what are the most relevant areas in each modality, giving interpretability. We do this by building the importance map that you can see here, and where the darker the region is, the more important and relevant the area is for the model. With this, we check that we get both good cross-modality knowledge, semantic understanding, and interpretability, which enables many other valuable use cases and downstream tasks that now Jakob is going to present to you.
Yeah, thank you, Gauthier. So Gauthier already showed you that our model is capable of providing general semantic understanding in form of correlations. However, of course, we want to go further. And especially when we ask ourselves the question that mainly drives us for this challenge, how can Lunar FM actually support science? And for this, let's consider titanium dioxide concentration on the moon. Titanium dioxide, or TiO2, is shown here in the image as this powder. And TiO2 as the combination of oxygen and titanium is important for construction, energy, and life support in general on the moon. In practice, people are most interested in describing and generalizing expert intuition, expert experience, or actual manual work. Or to state it differently, people are looking for hidden correlations in existing data examples, which would then allow them to draw conclusions on new data samples or data points. Here, we want to look at the titanium dioxide resources on the moon, the TiO2. Let's take a look at some positive examples where we know that with a given certainty, there's a high concentration of titanium dioxide. In practice, we also have negative examples as well, where the concentration is known to be relatively low. With our embeddings and these few positive and few negative examples, we can already draw conclusions and derive common characteristics and extrapolate them all over the moon. In this example, we apply simple principal component analysis on our multimodal embeddings and then separate the positive and negatives embeddings based on linear discriminative analysis. To first reduce in order to first reduce the dimensionality of our embeddings and then separate them into negative and positive examples. And even with this small number of positive and negative examples, the extrapolation to the moon already correlates very good with the ground truth maximum concentration measured in individual chips. Here, in this example, 25 positive and 25 negative samples results in more than plus 0.7 correlation with the maximum TiO2 chip concentration. So to summarize this, from only these few examples and very basic analysis tools, we actually derived a reasonable static map for potential resources. And with this, I hand over to my colleague Sumit.
Thank you, Jacob. This is powerful, but it's still a static map. But one more thing. The real future is interacting with this knowledge. So what if we could just talk to the moon? This is a short teaser of our lunar analyst agent. As you can see, one can use plain language to inquire about different regions of the moon based on their location or features. Here we are asking the agent to find regions similar to a known high titanium site based on geophysical models from the scientific literature as a guide. In the backend, the agent is using our foundation model as a tool to perform this analysis in real time. Therefore, this is how our analyst enables us to talk to the lunar data using natural language as a medium. So what have we delivered? Not just a model, but a new capability stack for lunar exploration. A unified data stack, the core multimodal embeddings, high confidence prospectivity maps, and a prototype for agentic analyst. This is our contribution, but it's just the beginning. So what's next? We plan to release our Lunar FM for evaluation in October. We welcome the entire lunar exploration community to join us to test the capabilities of Lunar FM and build upon it. Last but not the least, we would like to thank all of our faculty, advisors from ESRIC, LSA, Datarock, and our compute partners, ScanAI, NVIDIA, Google Cloud, for making this a reality. And this concludes our update. Thank you.